The following is a video presentation on the concept design and experimental work that was involved in the development and characterization of an AC to DC power supply. This was a requirement of Electronics 1 at Oregon Institute of Technology. So we'll start here. So an outline of what we'll be seeing here today. Go through the project specifications, project design, including all stages of the power supply, show you some experimental measurements and talk about some results, and then finally David will walk you through a video demonstration of the actual power supply. So the specifications, we were to design, simulate, and experimentally test an AC to DC power supply using a linear voltage regulator. We were not allowed to use an IC voltage regulator. We were to provide an adjustable regulated output voltage with current boosting and short circuit overload protection. The input is your standard outlet, 120 volts, 60 hertz AC. The output voltage was a 5 to 10 volt DC, and the max output current is half an amp. So this is your typical components of a power supply. As you can see here, this is our transformer. It's going to be a step-down transformer, reducing the input, reducing the outlet voltage from 120 to about 20. It's then going to be rectified using a full wave rectifier. Finally, we'll put a filter on here, smoothing out that signal, and then the regulator will go ahead and have a nice linear DC signal coming out to the load. So starting with the transformer. As I said, on the primary side of the transformer was the outlet, so 120 VRMS. The output is 22 VRMS. And the graph here is showing you the graph from the simulation. So the black is the primary side, the red is the secondary side. So the next portion of this is the bridge rectifier, and so what this is doing here is it's going to prevent any sort of prevent the negative signal from appearing, and so what it's doing is blocking that negative signal. So at which point now, as you can see here on the graph by the red waveform, we no longer have any change in polarity, and thus this signal is now considered to be a DC signal. As you can see, the red waveform, like I said, that's the rectified signal. The black is coming from the secondary side of the transformer. There's a slight variation in amplitude, and that's going to be due to the two diode drops within the bridge rectifier. So each diode has a drop of about 0.7 volts, so the two of them add up to 1.4, and that's what we're seeing here with that small change there. So moving ahead, the next part is going to be the power supply filtering, and so really what's happening here is this is going to be used to filter and smooth that rectified signal. And so what's happening is that the stored energy in the capacitor is being discharged during the charging cycles. And that's going to leave us with what you're going to see here in this dashed line. So you can see it never really dips back down to zero. It stays at an elevated level. For us, this was right around 20 volts. And as far as this peak-to-peak ripple goes, that is really dependent on your design. So the equation for that is right down here, where the voltage ripple is going to be equal to your the current at your load divided by 2 frequency times your capacitor. In this case, the frequency was 60 hertz, and the capacitor that we chose to use was a 2.2 millifarad. And just on that note, typically you are going to really want to choose a large capacitor, and that way the capacitor doesn't discharge too quick, and that's the time in which it takes to discharge is going to be down here, where tau is going to be equal to RC. So this here is what we were seeing in our simulation. This is the signal coming from our filter. As you can see, we have about a 1.2 volt ripple, and this is dependent on the adjustability, which is why we're seeing a little bit of a fluctuation there as well. All right, here's the actual schematic and design of our the first part of our supply. So you can see that here's the transformer. It's taking the 170 VRMS, stepping it down to about 20, and then leads into the full wave rectifier here, and then going into the peak detector filter portion of it. This resistor here, RB, this is our bleed resistor, and that's really just going to allow, once the supply is turned off, it's going to allow the capacitor to discharge through that resistor. All right, so going into the voltage regulators, there's two forms of a voltage regulator. There's a shunt or a series. So in the shunt regulator, circuit is connected in parallel with the load, as you can see here in this schematic. And basically what's happening here is the objective of the shunt regulator is to maintain a constant supply voltage at the load, and so this is accomplished by requiring a current IS to flow through the regulator at all times. If that load current is increased, then we'll see a decrease in the regulator current, and that way the supply current will stay constant at all times. So the most common form of a shunt regulator is going to be the Zener diode regulator, and in this scenario there's an unregulated voltage that is going to be regulated by that Zener diode, which is in parallel with the load. So there's the main condition with this setup is that there's enough current that's going to allow that Zener diode to operate in its reverse breakdown. And when that's the case, any changes in current will result in approximately the same output voltage. So essentially, we have a voltage divider here, or I'm sorry, these two legs are in parallel, so any voltage that's seen at this Zener diode will be seen at the load. The Zener diode, any changes in current, as long as we're in that Zener breakdown region, will not have any changes in voltage. So we'll have a nice regulated signal at the load. So looking at the series voltage regulator, you can see that the this configuration regulator consists of a variable element in series with the load. The regulating element will always see a voltage drop because it's in series with the load. So from this figure here, we can see that there's a voltage divider on the series elements, and the voltage at the load can be summed up as VL equals VT minus VS, where the VL is your voltage at your load, VT is your total voltage, and VS is the voltage drop at your regulator. So this next piece right here, this is the probably the simplest form of a series voltage regulator, and this is using a transistor and a Zener diode as a reference voltage, and the output voltage here is really what it's going to be is your the Zener voltage minus the voltage drop at your transistor. So VZ minus V base to emitter, and then that's going to be your output voltage. And so from here we can see that regardless of the input voltage, the output voltage will be constant, and once again that is providing that the Zener diode is in reverse breakdown. So some considerable improvements can be made to this design, including adjustability. So that's done by adding a DC amplifier or an op amp, and so this is going to utilize that Zener as a reference voltage, and then the adjustment of this voltage can be characterized here by V out is going to be equal to VZ times 1 plus R2 over R3. And so if you put a potentiometer in here for R2, you can adjust that gain. That's how we were able to do that with our design. So the addition of this op amp, however, results in the output being limited by Vin, where the Vin is what's powering this op amp. So the output can never go above what's powering this op amp. For our situation, that didn't matter. Vin was about 20 volts, and our max output voltage was 10, so that wasn't a problem for us. We're also going to see limited here where Vout can never be it's always going to be greater than the Zener voltage, so it can never go below whatever you choose here for your Zener diode. For us, we chose 5, and that was really to set up a baseline voltage and then see an increase from there, and we never wanted it to go below 5, so that wasn't going to be a problem for us. And additionally, the output current is going to be limited by the op amp's IOut max, and we use a LM741, so that IOut max is about 20 milliamps. So to compensate for this, what we did was we added current boosting, and so this is done here by adding this transistor Q1. And so the way this works is by adding this NPN follower, what we're going to do is we're going to boost that op amp's IOut max by a factor of beta. So that's going to give us a higher output current, but it is important to note here that this transistor is dissipating significant power, and as a result the transistor will get very hot. So here you should consider adding a heatsink to help compensate that. So now what we did was we added overcurrent protection, and that's done here by the addition of Q2 and this sensing resistor RCL right here. And so the way this works is that RCL is just used there, like I said, to sense a voltage, and once there's enough voltage to turn on Q2, Q2 is really just going to go ahead and rob the base current from Q1, and that's going to prevent any further increase of the output current. So all in all, the series regulator is more efficient than the shunt regulator, and it can be used for heavier load currents. And with the addition of a DC amplifier, current boosting, and overcurrent protection, it really enables this to be an effective circuit for many applications. So this is the overall design of our voltage regulator. And as you can see here, this is the simulation showing that the output voltage can be adjusted anywhere from 5 to 10 volts. And then finally, this is the schematic of the whole circuit put together. So transformer, full wave rectifier, peak detector, and voltage regulator. This is the actual circuit as was built and was used for testing. So this here is our transformer. Lead into the full wave rectifier. That's going to come in here to the peak detector, which is then going to go into the voltage regulator, which is all right here. This is Q1, here's Q2, and then here's our potentiometer that was used to adjust the output. And then finally here's our 20 ohm load. So this was some experimental measurements taken in the first round of testing. So on the left side, what you're seeing here on channel 1, that is the signal from the filter, and we have a peak of about 22.4 volts with a voltage ripple of 1.2. And then on channel 2, this was our minimum voltage at the load, so we weren't quite able to get all the way down to 5 volts, but we had about 5.6 volts showing here. And then on the right side, channel 1 is showing you the Zener diode, and as you can see, that is fixed at about 5 or 4.7. And then on channel 2, that is the maximum voltage at our load. So we were able to get to about 10. Here's some results, some comparisons between simulated values and experimental values. So everything's pretty much pretty close to what we were hoping for. All right, that's going to conclude this first part, and David's going to take you for a walkthrough through the actual circuit. Thank you.
All right. So here we have our 120 AC power coming in from the wall, single phase, and it's going to our transformer, which is rated 8:1 turns ratio, so it drops it down to approximately 22 volts. And what we have right now is the measurement of the full wave bridge rectifier on the screen. Right now it's running, but when you stop it, you can see how it's a full wave rectification. All right, and then right here you can see the peak to peak is 26.6 volts. So if you look in closely, you can see how it this was noted in one of the earlier labs, but when referenced, it drops below the 0 point, so it's actually accounting for a couple extra volts. But when we plug this in, now we are getting our circuit is being filtered. So turn this off, and input waveform number 2 is measuring across the capacitor. And as you can see, we have a steady ripple, and we have a max of 22.2.4 volts, and the peak to peak is about 1.2 volts. So if you look closely, you can see. Alright, so we'll be able to see the ripple when we zoom in. There we go. A little blocky, but there we have our voltage ripple. Very nicely pixelated. Okay, so moving on, at oscilloscope number 3, at probe number 3, it's measuring the voltage at the Zener diode, and this should be approximately 5 volts. As you can see, it's fluctuating between 4.8 and 5 volts. This Zener is rated for 4.7 volts, so. Alright, so we disconnected some of the probes on the oscilloscope and hooked up this DMM to our load resistor right here. And so when we adjust the potentiometer right here, the adjustable gain, you can see how we have a range of approximately just under 10 volts and all the way down to just over 5 volts, 5.27. So here we go. All right, and for the current, okay, so our 200 milliamps. Go up to our max is 369 milliamps, so not quite 500, but stays within the guidelines. And so as you can see, our circuit behaves appropriately but not perfectly.